Welcome to lecture 3 on the topic of transformers, and specifically in this lecture we're going to see transformer with core losses, and it is on load. So in the earlier lecture we had seen transformer with core losses on no load, but now we are seeing on load. So what happens if we start loading the transformer? So let me just explain the theory first. So you know the transformer to be. Let me quickly draw the transformer like this. So this is the core, and then you have the primary winding here, supplied by rated voltage V1, which is equal to E1. So this is plus minus, and then in the secondary side you get E2 is the EMF induced like this. So earlier it was no load, so therefore the switch was open. But now if I close the switch, I start getting some current flowing into the load. And here the flux is fine, and then when the switch is open, the current here we denoted as I naught. Okay, and then we had the vector diagram for this, that is I naught and V1 are not exactly 90 degrees apart, but I naught is nothing but IW plus I mu, that is the vector addition, and as a result of this we get I naught and V1 not being 90 degrees apart, and so on. Now we'll discuss what happens when this is loaded. Already in one of the previous lectures I had talked, when this is closed then we get I2 into the picture. So I'll explain it through vector diagram. So let me just use this space. So here I have V1, which is equal to E1, which is equal to the supply voltage. As a result of this supply voltage, there will be some current I naught, and the horizontal component of that I naught is I mu, which is the magnetizing current, and then the vertical component of that here is this one is IW. Now on the other side, we represent E2 is the EMF induced in the secondary side. Now if I close the switch, then there is going to be the current I2 into that. So I close the switch and the current I2 is flowing. Now what will be the relation of I2 with respect to E2 in terms of phase? What is the phase angle between I2 and E2? Well, that depends on the nature of the load. So if the load is purely resistive, then I2 and E2 will be in phase. And if the load is purely inductive, then I2 will be like this. So this E2 is leading and I2 will be lagging the E2 by 90 degrees. And if the load is purely capacitive, then the I2 will be like this. This will be the I2, and so on. So the I2 can take any value around E2. So this one is partly resistive and partly capacitive because I2 is leading the E2, and here I2 is lagging the E2, and so on. So depending on whether the load is leading, lagging, or load is unity power factor, or in other words load is resistive, the relation between I2 and E2 holds. Also the magnitude of I2 depends on the amount of impedance. So if the impedance is higher, then the I2 will be smaller, and so on. Alright, so therefore because I2 can have any phase, so let's first consider the case. So case A, where load is resistive. So when the load is resistive, what happens to the load current? So the load current I2 will be in phase with E2. So let me draw the load current like this, I2. So of course the scale for this amperes and the scale for the volts will be different, but here the important is all the currents should have the equal scale, and then all the voltages should have the equal scale. All right, so I2 is a current here. Now, as a consequence of this I2 flowing, we had already discussed I2 will set up its own flux phi 2, and because the current is varying flowing into the winding, so it will generate its own magnetic flux. Earlier, when the switch was open, I2 was 0 and phi 2 was also 0, but because the switch is closed, I2 started flowing and flux started coming up. This flux will reduce the main flux, and the main flux will momentarily fall, and therefore the E1 will reduce. Therefore, V1 is higher than E1, so sudden rush of more current, additional current will happen from the primary side. That additional current is I2 dash. So let me draw that additional current here, I2 dash. Now that additional current I2 dash, when I add to the original current I0, is my final current I1. So I1 is I2 plus I0, and this I0 itself is IW plus I mu. Now, what is the magnitude of I2 dash? So because E1 has reduced and there is a more current is flowing in, that will set up its own flux phi 1 such that the flux phi 1 cancels out the flux phi 2, thereby restoring the original flux phi which was set up under the no load conditions. Therefore, pretty much when the load varies also, the I2 varies and phi 2 varies, and accordingly I1 also vary, and ultimately it cancels out the flux, thereby restoring the same flux at different loads. So therefore the core losses are constant for the transformer, as we had discussed before. Now this I1, what is the magnitude of this I2? So it should be such that if the number of turns are N1 here and number of turns are N2 here, the ampere turns setting up here is I2 N2. These ampere turns have to be cancelled out by the ampere turns of I2 dash and N1. So therefore, to get I2 dash, I just have to multiply I2 with N2 by N1. So if I do this, then I'll be able to calculate I2 dash. Another thing is the sign. So if this I2 is and I2 dash should be opposite to each other. So therefore somewhere I should put a minus sign, because the addition of these two will be 0. So therefore they are cancelling out each other. So therefore I put a minus sign somewhere. So I can put this minus sign. But then we don't worry about this minus sign, because in the vector diagram we'll take care of it. So how we'll take care of it is by drawing the I2 vector on the opposite side of this one. So this is I2. Sorry, I2 dash. So I2 dash will be exactly 180 degrees from the I2. This is exactly opposite to that. Now this I2 and I0 should be added. So let me again put up some dotted lines. Although it looks like a gap, but it's exactly in phase. So I'll just move this to here and move this to here. So then this addition of these two will be my final I1 current. Now we had already seen before what is this angle between V1 and I0. This angle we are calling it as phi naught. Now therefore by that logic this angle will be phi 1. So this is the actual V1, I1 and cos of phi 1 the actual input power. So with this, this is the situation where we have the case where the load is resistive. So we can, when we come to numerical examples, we will do all the calculations and find these angles and everything. But as far as this vector diagram is concerned for resistance load, we should be comfortable with this. Now let's go back and take a different case, case B, where load is inductive. Not purely inductive, just when I say load is inductive, it has some resistance also. So let's draw the vector diagram. So this is V1, which is equal to E1. This V1 equal to E1 only applies as long as we are not considering any voltage drop in the primary winding. We are not considering any voltage drops here. So, but later on we will be considering voltage drops. Then V1 E1 will also uh, be varying. Then I have, this is my I mu and this is my IW, and as the addition of that I get, sorry, I get I naught. Now on the other side I'll have E2, which is exactly 90 degrees behind this and like this. Now the relation between E2 and I2, I said because the load is inductive, the current will lag the voltage by some angle. So how do you know the current is lagging the voltage? See all the, so if I take a reference point here and then look at this. So if I, this is my I and you are looking at this vector diagram. First I, all the vectors are rotating like this. So first E2 will come to me and then I2 will follow. So that is why we say that E2 is leading and I2 is lagging. So anyway, let's undo this. So this is I2. And this value phi 2 will be given by the load. So in the load power factor, whatever it is there, according to that I'll get it. Now this I2 exactly 180 degrees opposite to that I2, I'll get I2 dash. And this angle will be 180 degrees. And what about the length of this I2 dash? So I2 dash will be I2 multiplied by, I just defined earlier, N2 by N1. N2 by N1. Because I2 N2 is ampere turns and I1 N2 dash is ampere turns. Then I add these two. So let me not write it here. 180 degrees. Now let me add these two. And then finally I'll get I1. And this angle between I1 and V1 is phi 1. So this is the input power factor. And between V1 and I2 dash is phi 2. You can just look at it because the same angle is like this. So it is, so this is phi 2 and this is also phi 2. So you can just verify yourself in the diagram. Now let's do one more quick vector diagram, that is case C, load is capacitive. So if the load is capacitive, what happens? So again, this is my supply voltage and this is the I mu magnetizing current. This is IW working component of the current, and then this is I naught, that is the no load current, and this is cos phi naught everything. And then I have E2 exactly opposite to that. Now the I1 will be leading E2, sorry, I2 will be leading E2 by cos phi 2. So it will be this side. And then exactly 180 degrees opposite to that, I'll have this is I2 dash. So the magnitude on we can find out. And this angle will be phi 2. And then if I add this and this, so the resulting current will be I1. And this angle will be phi 1. So this is the capacitive, is a vector diagram when the load is capacitive. So using this vector diagram, we can really understand what is going on, and it is very nice to do this. So also another thing we had noted before, that the practical modern transformers are designed such that this I naught is very, very low. They use very good material, and they reduce the hysteresis losses, they reduce the eddy current losses. All these losses are reduced to such a level that this I naught is almost 1% of I1. So here it looks like I naught is very big, very big fraction of I1, but then it is actually negligible. So let's do one more set of vector diagrams. So vector diagrams neglecting I naught. So this is transformer on different loads. Transformer on loads. So let me do that here. So first is resistive load. Next is inductive load. And finally capacitive load. So V1 equal to E1, and luckily we don't have any I naught current here. So I have E2 here. Now because it is resistive load, I2 is in phase with E2, and therefore I2 dash is in phase with V1, and finally this itself is the vector diagram. So V1 I2 dash, it will be like that, and then the magnitudes and the lengths and all you can calculate. So this is the vector diagram under resistive load by neglecting the, so I have written neglecting I naught. So I naught is typically only around 1 to 2% of full load current. So we can afford to neglect it sometimes, or at least here just for understanding. Now let's do one more diagram with inductive load. So this is V1, and which is equal to E1. Then I get E2 here. Also the length of E2 and E1 also function of the number of turns N1 and N2. Now because it is inductive load, I get lagging current I2, and exactly opposite to that I get I2 dash. So this is exactly opposite. So 180 degrees. This is phi 2. Therefore this is also phi 2, which is equal to phi 1. And I2 dash is equal to I1, by the way. So because actual I1 is what? I2 dash plus I naught. But then since this is equal to 0, I2 dash equal to I1. So that way. So this is vector diagram for inductive load, and finally for capacitive load it is something like this. So this is V1, this is E2, and capacitive load the current will be leading. So this is I2. Exactly opposite I'll get I2 dash, and this angle is phi 2, this angle is phi 1, which is also equal to phi 2, and that's it. So this way we can get the vector diagram. So I hope you have understood the vector diagrams. Looking at vector diagram, we can understand what is going on in this. And in next part of this video, we'll solve some example problems, and then we'll all cases we'll solve resistive, inductive, capacitive, and then we'll try to gain some more understanding through solving the examples. Okay, so now we come to example problems. So this is problem time. We had discussed about transformer on load and how different power factors and different loading conditions affect the primary current. So we have a problem on screen. So you can pause the video, you can go to the problem, try to attempt to solve it, and then later on you can compare your answer with my answer. So let's get started. So we have a single phase transformer with a ratio of 550 and 110 takes a no load current of 6 amperes at zero point 0.2 power factor lag. So I have I naught equal to 6 amperes, and then cos of phi naught I have 0.2 lag. If the secondary supplies a current of 120 amperes at zero point 0.8 power factor lag, so I2 is 120 amperes, cos of phi 2 is 0.8 lag. So this is important, lag. Estimate the current in the primary. All right. So let's first start by forming the vectors. So I have this vector V1. So although I'm drawing it like this is my reference. So V1 equal to E1 equal to, the angle will be 0 for this. This is my reference. I start measuring angles from this as a reference. And 550 by 110. So this is 550 volts as given in the question. Now I naught is 6 amperes. But what is the angle of this I naught? So cos zero point 0.2. So first I'll get the phi naught value. So phi naught value is what? So this kind of problem, it is nice to, instead of doing individual calculations, nice to write a small code. So transformers lecture, I think we are in lecture 3 and this is example 10. So I'm just adding the problem number and the data that is given to us. Let me just work with that. So first I want to find out the phi naught. So PHI 0. So phi naught is nothing but A cos. So A cos is the cos inverse of 0 0.2, sorry 0. What is the power factor? 0 0.2 lagging. Okay. So this one I want to multiply by 180 and divide by pi to convert it into degrees. So let me execute this program. Okay. 78.4 I am getting. Okay. So let me write it here, the angle 78.4. Layer got selected. Okay. So 78.4 degrees is the angle I'm having here. Okay. So now cos inverse of 0 0.2. So that is 78.4. So therefore I can write I naught as a vector, that is 6 angle minus 78.4 degrees amperes. Now next is I2. So what is I2? I2 is, so if I draw a line like this is E2, this is 110 and I2 is 120 amperes, which is lagging at 0.8 power factor. So what is cos inverse of 0.8? So phi 2 equal to A cos of 0 0.8. So again into 180 divided by pi. So this will give me the value of phi 2. That is 36.87. So this angle measured from E2 is 36.87 degrees. So I can use a minus sign here because I am referring E2 and then I am going back one. In fact, even this is minus. So here you can see minus. So this is the reference. Now I transfer I2 to the primary side. That means I go for the I2 dash. So I2 dash, you notice the voltage magnitude is going from 110 to 550. The voltage is increasing. So therefore the current will reduce. So here I am writing I2 is 120, angle is minus 36.87. This is with reference to E2, this angle. But because now E2 will go towards, if I reverse E2, it will coincide with V1. So therefore I2 dash is nothing but I2 multiplied by N2 by N1, which is nothing but V2 by V1. So that is nothing but 120 multiplied by 110 divided by 550. So it will have the same angle, minus 36.87. This is with reference to I1. So here, let me write it. That is I2 dash. So I2 dash, I2D equal to 120 divided by 120 multiplied by 110 by 550. So here I'm just only calculating the magnitude. So I'm getting 24. So this is 24 and the angle will be minus 36.87. So this angle will be that 36.87. Alright, so this is 24 amperes minus 36.87. So now I have both defined. So what is the next job is to find I1. So nothing but I2 dash plus I0 dash. So I have to add the two vectors. So this is 24 amperes at minus 36.87 degrees and this is 6 amperes at minus 78.4 degrees. So this is the straightforward addition of two polar quantities. So for doing this, we need to represent these two as vectors. So let me represent that. So I naught equal to, the magnitude is 6 and I say exponent into I to the power of the angle. What is the angle? 78.4. So minus 78.4. So here I convert it to radians. So divide by 180 and multiply by pi. So I am just calculating I naught in complex quantity. So this is what is I naught. Similarly, I can calculate I2 dash. So actual quantity is 24 and then multiplied by exponent I multiplied by, so I is square root of minus 1 as you know, minus 36.87. So divided by 180 and multiplied by pi. This will convert it into radians again. Alright, so now if I run it, so I see I naught is this and I2 is this. So let me add a clear screen at the beginning. So here you can see I2 dash is 19.2 amperes minus 14.4 J amperes. So I have these two currents. So now I can find easily I1. So I1 will be I2 dash plus I naught. So now if I run it, so I got this I1 current. Now this I1 current, I want to express it as a polar form. So I'll just simply display absolute value of I1 and then angle of I1. So this angle will be in radians. So multiply by 180 by pi to convert it into degrees. So and then here will be my answer. So 28.7 angle is minus 44.818. So 28.7 angle minus 44.818. So this is again with reference to V1. So in other words, let me draw it a neat vector diagram. So this is V1 and I have, in fact I'll draw it to the scale. So it should be 4 times longer actually. So this is I naught, which is magnitude is 6 and the angle is minus 78.4 with reference to V1. Whereas the other one, this is I2 dash. This is 4 times bigger than this. So 24 amperes. Angle of minus 36.87 degrees. Again with reference to this. So this is the angle for this. So this is actually phi 2. This is actually phi naught. Now when I add these two, final solution which I got is something like this. This is I1 and this angle is called phi 1. And what was I1? We got 28.7 at angle of minus 44.818 degrees. So what is the power factor of the primary? So the power factor of the primary is cos of 44.818 degrees. So let's see what it is. So here also I'll just write it. Cos of angle of I1. So here I will not convert it into radians, degrees. Let it keep it in radians. So you're getting minus 0.71. So 709 is approximately 0.71 lag. So one thing you will notice is that the power factor of the secondary is 0.8, which is better power factor compared to the power factor of the primary, it is 0.7. So power factor is kind of suffering here. So I hope you also solved this problem and you also got a similar answer. So with this understanding, let's move forward and look at the next question. Here you notice everything is exactly same. A single phase transformer, same data. Only where it is different is at this point. Earlier the power factor was lagging, now the power factor is leading. Only this is a change. So the I naught current is exactly same. So I'll just copy the I naught current from above. 120 minus 36. Sorry, the 6 minus 78.4. So if I answer this, so I naught is 6 amperes minus 78.4 degrees. This is exactly same as example 10. Now I2 is different. So I2 120 amperes. So therefore the voltage is 110 at 0.8 power factor leading. So it will be 120 amperes plus 36.87 degrees. So because angle phi 2 is positive with respect to E2 as power factor is leading. So now what is I2 dash? So I2 dash will be 120 into 110 by 550 and the angle will still remain same plus 36.87. This will be with respect to E1 now or V1. And this one is 24 as we calculated plus 36.87 degrees. So now if I draw the vector diagram, it looks something like this. So the vector diagram is so this is V1. Actually V1 only up to here. So let's take this as E2. Now because this is E2, I2 is leading, so I get I2 here. This is 120 amperes and this angle is 36.87, that is phi 2, and that is positive. So here I get I2. So the length here is 24 amperes and this angle is 36.87. On the other side, I have I naught is 6 amperes and the angle is minus 78.4. So now I have to add these two vectorially to get the final solution. So to do this, I'll just, so finally let me write, okay, I think, okay, so let me write the formula. So that is I1 is nothing but I2 dash plus I naught. So I2 dash in our case now is 24 amperes at an angle of plus 36.87 with respect to V1 and I naught is 6 amperes minus 78.4 degrees. So I'll go back to my earlier code and then since I have everything here, I think I just have to copy from here I'll go to a new file, save file as. So this I'll call it as 11. So all this above calculation I don't require now. I think these three. So instead of minus 36.87, I'll just keep it plus 36.87. And then you notice, so I1 I got here, so this is I0 and this is I2 dash, and then I1 current I got it here. And final, when I convert into polar form, I got the current like this. And then the power factor is also 0.927. So it all works out together. So just take a moment, look at what we have done. 6 exponent of minus 78.4. By the way, if you did not understand this step, so let me write it. So this is nothing but, mathematically, this is 24 e to the power of j theta, that is j into 36.87. So this is the mathematical notation of this polar number. So 24 multiplied by e to the power of j. And similarly 6 multiplied by exponent of j 78, this is minus of course, minus 78.4. So if you have calculator, you can actually type this exponent to the power of j is actually square root of minus 1 and then 36.87, and if you actually do this, you will get the solution. So what is the solution we got? So individually I find I0 and I2 dash, then I added I, and then finally I got I1. So I1 I am getting 22.115 amperes at an angle of 22.66 degrees. So actually if you notice, the I1 is going to the leading side. So somewhere like this. This angle is phi 1 is now positive. Alright. So what is the power factor? Cos of phi 1, I am getting 0.922. So this is lag. I'm sorry, lead. Is it lag or lead? I think it is lead. Because the angle is positive. So therefore the power factor is leading. So what do you notice? So observation. So it is very important when you solve these problems, not only you just solve the problem, you also make some observations. So the first observation is, if load is lagging, then the power factor of primary is worse, or in other words, it is lesser than power factor of secondary. Because transformer itself is a lagging element, it is inductive, and the load is also inductive, so therefore primary is even more inductive. And the other observation is, if I don't have place there, I'll just write it here. Observation. If power factor 2 is leading, then power factor 1 is improved and leading, and may also become leading. So not only that, if you look at the actual active power delivered. So what is active? For a brief moment, I go back to exercise example 10, previous example. What is output power? So let me write it here. What is P out or P2? P2 will be V2 I2 cos of phi 2. And what is P1? It will be V1 I1 cos of phi 1. So let's calculate input power and output power. In fact, just look at the magnitudes. So these two are supposed to be equal if there are no losses in the transformer, but there are slightly amount of losses we are considering. So, all right, let's just find this. What is V2 I2 cos phi 2? I'm going back to my previous code. So, P1 equal to. So, what was my V1? 550. So, 550 is the first voltage of V1 into what is I1. So, how much did I get I1? I1 I am calculating anyway here. So, I'll just write absolute value of I1 multiplied by cos of this angle, that is my power factor. So when I do this, I'll get what is P1 and then active power P2. What is it? So this is 110 multiplied by, so I know it is 120 amperes, that is given in the question, and power factor also given in the question, that is 0.8 lagging. So given this data, now if I run this, so I get P1 and P2. So it's just a problem with display. So what is P1? It is 11,224 watts. Okay. So and then P2 is 10,560 watts. And then what is P1 minus P2? So this is loss. So here 663 watts is the power loss, and this loss will exactly match with the working, that is core loss of the transformer. So what is P naught? So P naught is nothing but V naught into I naught, sorry, V1 into, so what is V1? 550 multiplied by what is the no load current, that is 6 amperes, and cos of phi naught, that is 0.2. So it should match with this. So moment of truth, so let's run and see whether it matches. So it's almost matches 660 and 600. The variation, the 3 watts, is only because of the rounding of error that we are doing in our calculation and nothing else. So this is about what is going on. Now coming to the next problem, if I copy the same for the problem 11, that is example 11. So here what are the changes? So I think I1 exactly is same, P2 is same, and so on. So now if I run 550, 120, okay, yeah. So now also the same input power, the same output power and everything, but we are able to send the same input power but with less current. So 22 amperes is the current, whereas in the previous example, what was the current? 28 amperes. So my magnitude of current has reduced because of the improvement in the power factor. So I hope you're able to understand the comparison between 10 and 11. So try to do this. So just let me, for the sake of completeness, I'll write it here. V2 I2 cos phi 2. I got, this is for the first problem. Yeah. Let me run it here. 11224. 11,224 watts. And here I got 10560. This is anyway fixed because the power factor is fixed. 0.8 leading and 0.8 lagging. And P naught is 660 watts. Now let's look at the next problem. So again, to our surprise, or maybe as you expected, exactly the same problem, just the power factor is unity. So let's do that. So you can pause and try to answer this question, find out the primary current, and you can compare your solution with my solution. In fact, I strongly suggest you to do it right away and you compare your answer with my answer. Okay, so let me begin my answer. So again, if you look at the question, the same, the I naught current will be exactly same. So I'll write it here. I naught will be 6 at an angle of minus 78.4 degrees amperes. So this is exactly same. Now what is I2? I2 will be exactly 120 amperes with 0 degrees with respect to E2. This angle is with respect to E2. Now what will be I2 dash? I2 dash, it will just become 120 multiplied by 110 by 550. Angle will remain same but then the angle will be with respect to V1. We are just transferring, it's basically adding the minus sign. So by adding minus, by multiplying with minus 1, you are actually changing the angle by 180 degrees for a vector. So this is 24 angle 0 degrees. So how does the vector diagram look like? So this is my V1. This is E2. This is I2. This is I2 dash. And this was I naught, which is 6 angle minus 78.4. Is that so? I keep forgetting that. Yeah. And this is 24 angle 0 degrees. Now if I add these two vectors, I'm going to get a vector something like this. Of course, this angle won't be so high as I expect. Let's call this I1. So I1 is addition of I2 and I2 dash and I naught. So let's do that again in our code. I1 is I2 dash plus I naught. I copy this code here. Let's call it example 12. So what are the changes? So instead of angle I2 dash plus 36.87, I'll just give the angle of 0 degrees. That's all. Now if I run this, I'll get the final solution. So that is I1 is this one 25.2, and after converting into polar form, I get this 25.88 minus 13 degrees is the angle. So I1 is 25.88, angle is minus 13.12 degrees. So this is 13.12 degrees, angle phi 1. Then again you can see the input power. I think there's some problem here. The losses seems to have increased. So that might be because here I'm putting here 0.8. So that is not required. So output power is actually 110 into 120. So that power factor is not there. So now if I run it, so I'll get the correct solution. So the core loss is still 660 and that is matching, whereas P1, P2 are slightly different now because of the power factor improvement at the load. So I hope we have actually solved everything that is required in the question. So I hope you have understood these vector diagrams. It's very important to understand these vector diagrams, how they are doing. And then all three cases we have solved. This is the lagging case, this is the leading case, and this is the that is unity power factor case. Let's not stop here. Let's do some more problems on this particular theme, that is transformer on load, but only core loss is considered, copper loss is not considered. So we'll do some more examples. So let's do the next problem, that is example 13. And again, as usual, the procedure, you have the question in front of you, you attempt it yourself and try to solve it, and then you compare your solution with my solution. This is slightly different than the topic that we are discussing. Actually, here there's the power factor of load is not given, so I naught current is not given. It's slightly a different question. You should be quite flexible. Look at the question, and based on the given data, you should be able to understand what they are asking and then how to find it. So let's begin our analysis of this. The ratio is given. So n1 is to n2 is 30 is to 2. This ratio is given. So we know, or this is actually 15 is to 1 if you further simplify it. So you know that it is a step down transformer. The primary is high voltage and the secondary is low voltage. So, and the primary is connected to V1, that is 1800 volts. So right away I can find what is V2. So V2 will be 1800 divided by or multiplied by 1 by 15, or you can, using this ratio I can do that. So basically uh, it is this. So because I know it is step down, so the voltage has to reduce. So 1800 divided by 15. So let's try it here. 1800 divided by 15. So it is 120 volts. So far so good. So I got the this part of the problem. Also find the approximate winding currents on full load. Now to find the current, so you know that I1 is the summation of the I2 dash and then the no load current and all, but that information is not given. So the no load current is ignored. No load current is negligible. So therefore, I naught is equal to 0, and therefore I1 is nothing but I2 dash. Okay, so first, but then since it is given, find the approximate winding current on full load. So when the load is full, I know the kVA, I know the voltage, so I can actually find out the full load current. So I1 full load equal to, and then I2 full load equal to. So 120, that is 12,000 divided by, what is the voltage? 1800. So this will give me this is kV, this is VA. So divided by, let me write the ampere units, VA divided by V. So this will give me the amperes. 12,000 divided by 1800. So 6.67 amperes. Now this is the magnitude of the full load current, but I don't know what is the phase of the full load current. That information is not given. So although when the transformer is fully loaded, the kVA is given, but not the kilowatt. So we cannot calculate that. We'll be calculating at least this. So what is the magnitude of full load current in the secondary side? So I can directly do like this. Secondary side is 120 volts. So this is volt amperes and volts. So here I'll calculate. So this I'll get 100 amperes. Now the other way to calculate secondary current is through I2 dash. So what is I2 dash? So I2 dash is nothing but I2 multiplied by N2 by N1. So that is nothing but 100 amperes multiplied by 1 by 15. So the ratio. So this is 100 by 15. You will again get 6.67 amperes. That is nothing but I1 full load. So it's exactly same we are getting both. Let's move on. So I calculated this one. Finally, find the cross-section area of the core if the maximum allowable flux density is Tesla. So looks like we have to use the EMF equation. So let's write the EMF equation. So the induced EMF E1 is 4.44 multiplied by flux, that is, oh, I think there is a problem here. I'm not clearly knowing how many turns are there in the transformer. So without that, I may not be able to find this. So let me anyway write down the formula. So the frequency multiplied by number of turns in the primary and multiplied by flux density maximum and multiplied by area of cross section. So I think the question is a little bit flawed. I apologize if you found it trouble, but anyway, I should not be apologetic. If there is a flaw in the question, you should be able to detect that there is a flaw because the ratio is given. Not, I will not be able to find the uh, actual number of turns. All right, so there are two unknowns here. So therefore, one of them we will have to assume. So let's say n1 is something like 600. Let's assume. So if I do that, then from this, so what is E1? E1 is EMF induced in the first, that is nothing but 1800. So that is nothing but 4.44. Frequency is 60 and the number of turns N1 is 600 and then the maximum flux density is 1.1 Tesla. So finally this area is unknown. So let's calculate that. 1800 divided by 4.44 into frequency is 60 into number of turns is 600 into maximum flux density is 1.1. So I am getting like this 0.0102. Area is 0.0102 and this the unit will be meters square and that is nothing but 102 centimeter square. So this is my area. So this is what was asked in the question. Of course, just this small assumption that we need to make. So that we have done. So with this, we conclude this problem. So let's go to the next problem. So this also I found slightly interesting. So go through this question once. Try to understand the question and then try to solve the question and then later, compare your answers with my answers. Let's do it now. A transformer has 1,200 turns in primary and secondary respectively. So let me write the given data. So N1 is 1000 and N2 is 200. Load current on the secondary is 90 amperes at 0.8 power factor lag. So also given I2 is 90 amperes at 0.8 power factor lag. So from this I can write I2 is 90 and so 0.8 cos inverse 0.8 is minus 36.87. So why I am putting minus is because of the lagging power factor it is given. And all power system engineers should know this by heart. Cos inverse of 0.8 is minus 36.87. So you can check it. So this is current. This is with respect to E2. So I2 is given in the question. The primary current is 24 amperes at 0.707 power factor lag. So I1 is equal to 24 amperes at 0.707 power factor lag. Notice that the power factor of the secondary is 0.8 and the power factor of the primary is even worse than 0.8. So which confirms because the secondary is a lagging power factor load. So the primary will have even lesser power factor as we are able to see here. And 0.707 again should be familiar to you. So it will be 24 at an angle of minus 45 degrees. So cos inverse 0.707 is 45 degrees. So this is I2. This angle is with respect to V1. Now notice this is slightly different than the previous problems that we solved. Determine the following: no load current. So now I want to find what is I naught. So we have to find what is I naught. So all the time we used to see the question what is I1, but here the question is different. We have to find I naught. And we know that I1 is nothing but I2 dash plus I naught. So right now these two are unknown. So let's first determine I2. So these are all again vectors as you are seeing. So let's determine I2 dash. So I2 is here. So what will be I2 dash? So I2 dash will be nothing but I2 multiplied by N2 by N1, because the ampere turns have to match. So that is 90 angle minus 36.87 multiplied by N2 by N1. So that is 200 divided by 1000. So I'll get 90 into 200 divided by 1000. So I'm getting 18 amperes. So this is my I2 dash. So therefore I naught, so I know I2 dash, I know I1, so I can find out I naught. So what is I naught? I naught is nothing but from this equation I1 minus I2 dash. So I just take this to the other side. So I1 already given in the question, 24 amperes at an angle of minus 45 degrees minus 18 amperes at an angle of minus 36.87 degrees. Now if I do this calculation, I'll be able to find what is I naught. So let's do that. So let's create a new file and we'll call this transformers example 14, I think. So here let's clear the screen and clear the variables, and let's define I1 equal to 24 exponent of I into minus 45 degrees. So I have to divide by 180 and multiply by pi to convert into radians. So this is I1, and I2 dash is equal to 18 exponent of I multiplied by minus 36.87 divided by 180 and multiplied by pi. So I get these two values. So let me run and see. So I got the value of I1 and I also got the value of I2 dash. So now it's a matter of finding I naught. So I naught is nothing but I1 minus I2 dash. So I want to display absolute value of I naught and the angle of I naught. We have done this several times. So convert into degrees. So let's run it. So that's it. I'm getting 6.68 amperes at an angle of minus 67.38 degrees. So this is the rectangular form of the current, and this is the active current. So in fact, looking at the rectangular current, I can also find, so I naught, finally after doing this subtraction, I got 2.57 minus J 6.17. So this is with respect to V1. So therefore this 2.57 is actually the working component of the current, and this 6.17 minus J means minus 90 degrees with respect to V1. So that is the magnetizing component of the current. So we are also able to get the components of the currents. And when I convert into the magnitude and angle, I'm getting 6.68 of the current, and then minus 67.38 degrees as my angle. So this is my no load current of the transformer. That means when the load is removed, only this much current will be flowing. So based on the information given, we are able to calculate that. So no load current and magnetizing current, working component of the current, we are calculating. Okay, no load power factor. So what is the power factor of no load? So that is cos of phi naught. So that is nothing but cos of this 67.38. So cos of minus 67.38. So this I want to convert into radians. So I have to multiply by pi and divide by 180. So I'm getting 0.384 is the power factor. It will be lagging, of course, because of the minus sign. This is the no load power factor of the transformer. So we have done this also. And finally, the last thing, core losses of the transformer. So let's calculate the core losses. So P naught is nothing but V1 I naught cos of phi naught. So therefore, V1 voltage, where is the V1 voltage? Oh, the V1 voltage is not given. So because of that, we cannot determine the core losses. Just assume V1 equal to 1000 itself. So if I do that, then I can calculate this. So this is 1000 and I1 I0 is 6.68 and cos phi naught is 384. So from this I get 1000 multiplied by 6.68 multiplied by 0.38462. I'm sorry, is it? Yeah, that's correct. So 2569. So this is watts. 2.569 kilowatts. So this is the no load power of the transformer. So really it should be a big transformer, because if it is taking 24 amperes at 1000 volts, that is 24 kilowatts. Out of 24 kilowatts, 2.5 kilowatts is kind of 10%, which is still quite high. But anyway, this is just assumed numbers, so we are not mapping it to any practical transformer. That's about this example. So let's, before we move forward, let's discuss the vector diagram of this so that we complete our understanding. So the question is, V1 was given to us, then I1 was also given to us. So what is I1? I1 is 24 amperes minus 45 degrees. So this current I1 was given to us, 24 amp minus 45 degrees. Similarly, this is E2 and I2 was given to us. So from I2, and this angle is phi 2, which is 36.87, and this is lagging. That's why E2 is leading and I2 is lagging. So I get the I2 dash. So this is supposed to be somewhere like this. Because I2 dash magnitude, I got only 18. Yeah, it is 18. And this angle is minus 36.87 degrees. So that is this angle. So I know this angle. Now, what is, so we should not add these two, because the I naught will be somewhere here. The addition of this I naught and this one is supposed to be the I1. So from this I naught, how do I calculate? I just take, so I take this and then subtract this. So this is minus of I2 dash. So I1 plus minus of I2 dash will give me I0. So and what is I0 that we had calculated? That is 6.68 angle of minus 67.38 degrees. All right. So this is one more example problem on transformer on load. So here notice what we are considering is transformer on load with core losses. We are not yet started considering the voltage drops in the transformer, that is because of the resistance of the transformer windings. We are not yet considered the copper losses in the transformer. We are only working so far with only the core losses of the transformer. So we may try, I mean depending on the time I'll have to check, I might do some more examples on this, or we might jump to the next topic, that is the transformer with resistance. So keep practicing these problems. So I am kind of explaining the concept followed by some numerical examples, and then keep practicing. The more you practice, the more you will understand this. Try to take, maybe I'd give it as a homework now. So try to take a sheet of paper. So this is homework. Those who are watching it on YouTube, so draw vector diagrams of transformer on load, that is capacitive, inductive, and finally resistive load. So consider no load current and neglect the voltage drops in windings. That means V1 will be equal to E1 and V2 will be equal to E2 if you neglect this voltage drops in the windings. The terminal voltage will be equal to the induced voltage. Thank you.